Hello friends. So now we'll start the concept of entropy, but before that we have to understand the concept of the Clausius inequality. What is Clausius inequality? Then after we can understand the concept of entropy. So uh, what is Clausius inequality? Let us try to understand it. So let us say we have a heat engine like this. We have a heat engine in which we have a source temperature at TH and sink temperature at TL, and we have a reversible heat engine which is taking QH delta QH amount of heat from source, and it is delivering delta QL amount of heat to the sink, and by their interaction it is producing del W amount of work. Fine. Then let us try to write a new term which we want to find out. Let's say I want to find out what is the value of del Q by T throughout the cycle, which is reversible. So what is this value? This value will be because this our system is this, so this system is taking del Q amount of heat. It is taking del Q amount of heat divided by at source temperature TH, and it is rejecting del Q L. This is del QH, del QL amount of heat divided by TL. This will be the value if you want to find out this value. Fine. Now according to Carnot's law, we know that the heat, whatever heat we are getting, that is actually proportional to the temperature of that system. So from here if we want to find out what is the ratio of del QH upon del QL, then that would come out to be TH upon TL. So from this we can write that del QH divided by TH is equal to del QL divided by TL. So now we can see that because these two terms are equal, so if we'll put it here, then we can get that for reversible process del Q by T is equal to 0. Fine. So this was actually for the case of reversible heat engine. So let us take it as case 1 for reversible case. Now we'll try to find out that value for case 2, that is for irreversible case, for irreversible engine. So now we'll try to make the engine something like this. Let's say this is the source temperature TH and this is the sink temperature TL, and let's say we have a reversible heat engine, fine, which is taking del Q amount of heat and it is rejecting del QR amount of heat, that is reversible from reversible heat engine, and it is producing del Q amount of work from the reversible engine. And we have also made a irreversible heat engine which is taking del Q amount of heat and it is rejecting del Q amount of heat for irreversible case, fine, and it is producing delta W amount of work. So now first of all we know that for reversible case the closed integral of del Q by T is equal to 0, or we can say that from this equation, from this figure, and for the case of reversible heat engine we can write it del Q upon TH minus del Q R rejected, which is reversible, divided by TL is equal to 0. So here we can write that del Q upon TH is equal to del Q rejected heat, that is for reversible, divided by TL. Now let's see for the irreversible case. For the irreversible case, if you want to find out the closed integral, that is del Q upon T, then we'll know that it is taking del Q amount of heat, this is del Q amount of heat from TH temperature minus del Q rejected in irreversible manner to lower temperature. Now let's say we have equation, this equation is first equation. Now from this equation we can write that for irreversible case we can write that we can replace del Q upon TH value. So we'll write it del Q rejected for reversible case upon TL minus del Q rejected for irreversible case upon TL. Fine. And now we know that the efficiency of a irreversible engine is always less than efficiency of a reversible engine, or we can write it 1 minus del Q rejected for irreversible upon del Q is less than 1 minus del Q rejected for reversible upon del Q, or from this equation we can write that del Q rejected for irreversible is greater than del Q rejected for reversible. This means that for the irreversible heat engine we need to extract, or we need to throw much amount of energy than the reversible heat engine. I mean more energy is wasting in case of the irreversible, that is obvious. So because that irreversible heat rejected is more, so for irreversible process, that is from equation here, from this equation, because TL is same and reversible is less, so we can write it as closed integral of irreversible del Q upon T is less than 0. This is the Clausius inequality for the irreversible heat engine. Fine. Thank you.